So as we were discussing, the partial discharge mechanism in itself is such that it can cause stress in the surrounding insulation. So whenever you have some small partial discharges happening within the void, within a void or within a small encapsulated or in a small region inside a dielectric material because of whatever local field enhancement, the possibility is that there would be stresses created which would impact the surrounding dielectric and may cause degradation thereof. Now, there can be various kinds of stress mechanisms at work here due to the occurrence of partial discharge. These are particle impact, thermal stresses, mechanical stresses, chemical stresses, and lastly, electrical stresses. So let us see what we mean by these various stresses and what they entail. So first, let us take the case of particle impact. Whenever you have a partial discharge, you are talking about charged particles which are being accelerated by the field, which are moving in the field, and they acquire energy from the field. So, and then they come and impinge. So when you have a void, let's say when you have a void discharging, the charge which was present at one end of the discharge channel will be accelerated through the gap towards the end of the discharge channel, and by the time it reaches the end of the channel, it can have acquired considerable energy from the applied electric field, and therefore it can impinge on the dielectric at the ends of the discharge channels with considerable energy. As a result, degradation of the surface is possible. What kind of degradation? The local molecular changes might occur in the impacted surface because the particles may happen to have enough energy to cause bond scission. And whenever there is a bond scission, there is the likelihood of there being some electron release. But remember, very high energies are required to cause substantial damage. So for example, if you look at this table, which gives us the chemical bond energies which are associated with epoxy resin, there are various kinds of bonds in a polymer. You have CH bonds, you have the aromatic CH bond, the methyl CH bond, methylene CH bond, CO, COO, CC. So various kinds of bonds are there, and each of these bonds have associated with it a certain energy that is required for this bond to be broken. So for example, the CH aromatic bond needs something like 434 kilojoules per molecule. For the ketone bond, we need 729 kilojoules per molecule. So we actually need this amount of energy for bond scission to occur. So electron energies in excess of 500 eV are required to cause substantial damage. Now, what kind of interaction will take place between the surface and the particles? It's difficult to predict. It depends upon the structure and the energy state of the surface of the species that are present in the impacted surface. It depends upon the particle energy. But the point is that it is possible that sufficient energy might be there for bond scission to occur. Generally, only through particle impact, you will probably not have significant damage. But we must remember that whenever there is any kind of stress mechanism happening due to PD, it is always associated with some other stress mechanism. And in the presence of a second stress mechanism, the particle impact may cause significant damage. So it is not impossible. Next, we come to thermal stresses. Now, when you have discharge happening, there would be energy that is injected in the vicinity, and this can result in temperature rise. For example, you have the gaseous environment, and this gaseous environment, because of the passage of current, gets heated up, evaporation occurs, more vapors are created, and this will travel to the nearby dielectric. You may have migration of gas molecules along the thermal gradient because there is a temperature difference from the near vicinity of the discharge to places far away. The temperature rise can cause chemical bond restructuring, so certain bonds might be broken, certain new bonds might be formed, exothermic reactions might happen. Now, if you look at thermal stresses are of interest mostly in the context of polymeric materials. Thermal stress which is created by partial discharge may be sufficient to cause damage to polymeric materials. If we are talking about other kinds of solid insulating materials, then thermal stress is not likely to cause a lot of damage. Even in case of polymers, right away, even if degradation happens, it may not be significant, but it may become significant over accrued damage over a long period of time, or if you have specific situations. So simple structures such as polyethylenes can degrade by random chain scission in the presence of heat. Depolymerization can occur and the polymer chains might fragment. Chain segments may fragment. So you end up with a strong polymer, and as a result of thermal stresses being generated due to PD, things may change and you are left with you don't have much of the polymer left. It is replaced by some other byproducts. After that, we have to consider mechanical stresses. Now, whenever there is a discharge, this discharge releases energetic particles. These are involved with the discharge and they go and impinge on the ends of the discharging channels. Once they reach there, these are charges which have considerably high energy, some of which is just expended by the time it reaches the other end, but it still may have energy sufficient for it to occupy any trap level which is present in the solid dielectric material. What I mean by trap level is unfilled energy holes, unfilled energy levels in the solid material. And when you have charged particles or electrons with energies very close to this energy level, the charged particle may give up some of its energy and acquire and come to occupy this trap level, and therefore it gets trapped. So whenever there is a discharge, there is always a very high possibility of the charges involved in the discharge to get trapped in the solid dielectric material in the neighboring region. Now, once that happens, you have a trap charges, and trap charges will apply a space charge field around it. On top of that, you have an applied electric field. And what might happen is that these trap charges and the applied electric field might interact with each other, and as a result, vibrational mechanical stresses may be set up in the dielectric material. There might also be local stresses due to the attraction and repulsion of trapped charges. So let's say there is one region where you have trapped positive charge. There is physically another region which has negative trapped charge, and there would be attractive forces between them. Or if they are both like charges, repulsion between these charges. So it might be that there are small forces being built which cause mechanical damage to the system or mechanical stress to the system. Apart from that, you can have impact of larger particles at the discharging surface. For example, there might be, it depends upon, of course, what kind of impact would there be and what amount of damage there would be, depends upon the mass number and the collision velocities of the particles. There might be chemical changes due to particle impact which causes mechanical damage. For example, it might affect the cross-linking in polymers. Materials may become more brittle or they may become less brittle. Stresses are unlikely to be so high as to cause fracture, though with sufficient energy, trap charges, attraction and repulsion between trap charges or impact of energetic particles can cause fracture of the surface. However, in practical situations, it is unlikely to happen. Then we have chemical stresses. Particle impact, thermal stresses, and mechanical stresses can all result in changes in the chemical structure. Various species may be generated, and these species may interact chemically with the solid and cause damage to the solid material. For example, if you look at ionic species that might be formed during DC coronas, in the column A, you have materials or byproducts which are created when the point electrode is negatively charged. So you have CO2 negative ions, CO3 negative ions, O2 negative ions, O3 negative ions, NO3 negative ions. When the point is positively charged, you can have O positive, O2 positive, nitrogen positive, nitrous oxide positive. You can have hydrogen positive, nitrogen positive, NO positive, N2 positive, NO positive, NO2 positive. All these different types of species might be formed, and some of these species may not be very good for the material from which it has been generated. So it's, for example, ozone. Ozone might be created when you have a negatively charged negative electrode at a very high voltages. So in that case, you have to remember that ozone is a very strong oxidizing agent, and as a result, you have air. Let's say you have air and ozone is created, and this O3 reacts with the oxygen, with the nitrogen that is present in the air, and it will produce oxides of nitrogen. Oxides of nitrogens are known to react in air to form nitric acid, and nitric acid is strongly degrading, strongly corrosive to the material around it. So what is happening in chemical stresses? One is various kinds of chemical reactions might take place such that the material that you start with, you end up with a different material. And moreover, some of the byproducts of these chemical reactions that are set forth might cause damage or changes to the surrounding dielectric material. Lastly, of course, we have electrical stresses. When you have charge deposition from a discharge, you have a space charge field. The space charge field is superimposed on the applied electric field. So you have a Laplacian field. On top of that, you have a Poisson field. So if these two fields aid each other, if they're in the same direction, then the field will be aggravated strongly within the entire material. And as a result, there might be local microscopic and macroscopic effects causing degradation. Local electronic breakdown can also take place around sites where treeing has taken place. So for example, let's say this is an example of a tree, and when you have at the ends of the tree channels, you will have trapped charges. So when you apply the electric field at the tip of these channels, there will be very high local field enhancement. So at those regions of local field enhancement, damage may accrue. The tree can continue to progress further till till complete failure occurs. That is a possibility. There can be other electronic breakdown mechanisms which can be set forth because the tree already has charged species inside it. The tree already has some damage, and there are charged particles inside the tree, and the tree channels discharge. So we have to remember that whenever you see tree, the growth of electrical tree in itself is inextricably linked to PD activity within the tree tubules. So let's say here you have an example of the same tree at two different points of time. These pictures are taken from Desado's paper of 1997, IEEE-DEIS. Here you see the tree has progressed to a certain degree, to a certain extent, and then as you leave this energized, you see a lot of PD activity taking place. This gives you the discharges per second over a long period of time. 2500 seconds, you see considerable PD activity taking place. At the end of this PD activity, what you see is, you see that the tree has grown considerably. It has become a completely bushy tree which has almost occupied the entire space in front of the needle, and then there are some filamentary channels which are continuing to progress and reach the other electrode, and the PD activity is continuing. The nature of the PD activity has changed, but there we still see PD activity taking place. So whenever you have electric tree, you have PD activity inside the tree channels. The first thing it does is it causes the PD to continue to grow, and if considerable growth happens towards the other electrode, ultimately complete failure might happen. Otherwise also, it continues to cause damage to the channel walls, and degradation may spread horizontally. So this video was created in my lab where we were filming a tree happening in an epoxy resin sample. We had a needle plate electrode, and the tree had already progressed to a certain extent. There was some filamentary channels created, and we were able to see partial discharges actually taking place inside the tree channels, and the channels growing larger, thicker, and broader. Now I'll stop here and show you exactly what this is. As you can see, this is the needle, and there is a tree which has progressed from the needle already. So these are some filamentary channels. Some of these filamentary channels and similar filamentary channels viewed with a high resolution camera can be seen here. What this huge thing is actually an air bubble. Now, if you can think about this air bubble as a storehouse of charge, there is a lot of charge inside because there has been discharges taking place. So there is a lot of charge, a lot of ionized air inside because we have applied electric field, there's a lot of ionized particles inside the bubble. So it is somewhat similar to the ground electrode, which provides as much charge as possible to the dielectric. But the advantage here is that we have been able to arrest the tree growth because below this bubble, there is considerable amount of material. The epoxy material is there between the ground electrode and the void. So as a result, even though the tree has actually bridged the bubble to needle gap distance, the activity is limited to the tree which is created on top of the needle to the top of the void, and therefore breakdown does not happen. Normally, once considerable PD activity begins inside the tree channel, the tree quickly goes to breakdown. So a puncture will happen and we will not be able to watch. But in this case, the void behaves like a barrier between the rest of the electrode material and the ground electrode, and we can concentrate on what is happening on top of the void. What is happening is you have these three channels, and here as you see this white region, this is where the partial discharge is taking place. So preferentially from there are many filamentary tree channels, but preferentially a considerable amount of PD activity is taking place in this tree channel. And you can see what happens next. When I start the video, so you can see that the discharge is traveling upwards. From the void, it is traveling upwards, so charge is flowing upwards, and wherever discharge takes place, after the discharge is extinguished, the channel becomes thicker. So the channel becomes thicker and it can no longer support the discharge, and then the discharge moves to a region where there is still a constriction. So it is as if somebody is digging a path from the needle electrode to the void, and this is happening through PD activity. See, huge PD activity taking place in a particular region, PD activity. So you can't probably see it very well anymore. Now it has moved to this region, and then this channel gets thicker and thicker, and then it moves here. So what essentially is happening is, when you have initially, if you remember, we started with a channel which was as filamentary as this subsidiary channel, and then because PD activity continued to happen within this channel, the channel become thicker and thicker, and now we really have a big eroded channel bridging the needle. The needle cannot almost be seen, bridging the needle and the void. The reason that we have been able to see this is because the void prevents the tree from reaching the other electrode and going to breakdown. So we can really see how PD activity takes place within the tree channels and what is the consequence of this PD activity. So we have seen that as a discharge takes place within the tree channels, degradation happens to the surrounding dielectric. Similarly, whenever you have any void or any encapsulation or any region where PD takes place, a similar degradation will happen to the surrounding region. So this is the kind of electrical stress we were talking about. Now, one of the very important things that we have to remember is the synergy of stress. When we are talking about material degradation happening due to PD in its vicinity or on its surface, we cannot really say that this is because of the thermal stress that was generated, or this is because of the electrical stress that was generated. It is generally a consequence of the synergetic interaction of all stresses which are responsible for material degradation. So there would be a unique and unpredictable combination of stress effects at any discharging surface. So whenever a discharge happens, thermal stress is generated. Because of thermal stresses, there are byproducts. These byproducts may be corrosive. These byproducts may cause chemical reaction at the surface. Because of temperature rise, there might be exothermic reactions. Because of these exothermic reactions, there might be trapped charges. The trapped charges may cause mechanical vibrations. So essentially, it is the synergetic nature of the discharge which causes the degradation mechanisms, and therefore, when PT causes damage, it generally doesn't happen very quickly. It happens over a long period of time, and that is precisely the reason why PD can be used as a condition monitoring marker, as a health monitor, because you get enough time to monitor the PD. And if you see that the PD is growing, if you see a particular pattern in which the PD activity is happening, this will give you an indication that something is wrong. It might even give you an indication of what is wrong and what corrective action needs to be taken. So it gives you a lot of time over which PD monitoring can give you a clue about the condition or the health of the equipment insulation. So the synergetic nature of discharge degradation mechanisms cannot be overstressed. One form of stressing does not in itself result in degradation, but that does not mean that you can dismiss it. It will be a contributory mechanism when there are other stress mechanisms present. Different materials, gaseous atmospheres, contamination levels, discharge magnitudes, and the discharge orientation, all of them will decide what kind of unique combination of stress will be there at the discharging surface and how that will affect the discharging surface. So there is no way to predict, but we can estimate what might be happening because we know what are the likely events that are possible. Next, we will talk about partial discharge measurements in the next lecture.